The method of sections is useful when we want to find the forces in specific members of the truss without needing to analyze every joint in detail. Recall that based on our assumptions to solve truss problems, the forces in trusses is axial forces, tension or compression. In the diagram shown, if we imagine a cut in the member will be separated into two parts. Each part is in equilibrium. This principle can be applied broadly to analyze and solve truss problems. The second method for solving truss problems. The method of sections. The method of sections states that if a truss is in equilibrium, then any section of the truss is also in equilibrium. Also, any joint is in equilibrium. Problem-solving strategy. First, we draw the free body diagram and determine the reactions in the external supports using the equilibrium equations for the structure as a whole. Second, we identify the members in which we want to find the axial forces. We separate the two parts, so the internal forces appear in each part as external forces, as shown in the figure. Each part is in equilibrium. Sum of the forces acting on it must be zero, and the sum of the moments must also be zero. Example, the section method. For the truss shown, determine the axial forces, N, in the members EC, CD, and DB. First, we draw the free body diagram and determine the reactions in the external supports using the equilibrium equations for the structure as a whole. The equilibrium in the x direction yields xa equals 0. The equilibrium moment about point A gives Ne equals 1150 Newton. The equilibrium in the y direction yield Ya equals minus 250 Newton. Next, we can imagine making a cut through the truss passing through the members EC, CD, and DB. This cut divides the truss into two parts, one part on either side of the cut. Each part is in equilibrium, sum of the forces acting on it must be zero, and the sum of the moments must also be zero. In general, we choose the part with fewer forces. In this example, we use the left part to do our analysis. The moment about point C eliminate the forces in TCD and TCE, we obtain TBD equals 333 Newton. The equilibrium in the y direction yield TCD equals minus 883 Newton. Finally, the equilibrium in x direction gives TCE equals minus 933 Newton. If we assume we are interested to find the forces in the members CB and AB, then we isolate the joint B, which is now having only two unknowns.